Okay, so I'm going to talk about data-centric parallel programming and focusing on various aspects. But let me first motivate this a bit, talking about the physics of computing. So this is actually something that I find incredibly exciting. I hope I don't spend too much time on it. So one of the things is, that we all know is this diagram, right? So we've all seen it. Can you see my mouse, by the way, Hatem?
Yeah, yeah.
Okay, perfect. So we all know this diagram. We actually all know this diagram until this bar here, which I drew, and then I continued it for the heterogeneous. So this was all CPU back here before 2011. And here I drew it for GPU or any kind of accelerator, also including FPGAs and other ones. And there you can see what actually happened is that the sequential performance dropped quite massively. Well, on the CPU it basically went flat, but for accelerators it dropped, and the numbers of cores went up extremely massively. So this is something that happened, basically happened as a reaction to some event that was earlier, the end of Dennard scaling. So this is Mr. Dennard here. The end of his predicted scaling, which basically predicted that we can extract more compute performance, or that the energy needed for compute scales proportionally with the process. That unfortunately ended in 2006. Then we all know Moore's law, which is a little bit better known. That ended later. That is still, people still say it's alive, but the company who mainly says that it's still alive just had a major stock problem 2 days ago. So we may or may not believe that they are right. I personally am not a believer. I think it's really dead. But there are still people arguing that Moore's law is going strong, and it may continue in some aspect, but certainly not for long. So this is the foundational observation. So this is the empirical observation. But where does this come from? So this basically comes from the fact that we have been working in computer science with scalability. So we scale down the process technology to smaller and smaller and smaller elements. In fact, TSMC just announced a 5 nanometer process. They have a roadmap that's going down to 3 nanometers, but at some point there is an end. 0 point some nanometers is the size of an atom. And we need more than one atom to switch voltage. And the nice thing is you can actually see, so I'm giving a bit away from me. So I entered that game at 45 nanometers. So I'm not that old. And for that process technology, we can exactly see the energy consumption for an addition, a multiplication, but also the energy consumption for moving data. This is the last published number, by the way, from 2014. So this is very conservative, a very conservative business about releasing numbers. So here we see that for an addition, we need essentially 1 picojoule. But to move the values from level 1 cache, so that's like the closest cache you can have, you need already 10 times as much. Moving them from main memory, you're basically 1,000 times off. Right? So this movement is extremely expensive. Now the question is, where does this come from? Well, there are 2 physical laws that we should know about as good computer scientists. So one is the Landauer limit. So the Landauer limit is a fundamental physical constant, which is the minimal energy required in order to create or remove 1 bit of entropy. Right? So this is an extremely important constant. The good news is that this is 3 times 10 to the minus 21. And we are a couple of million times away from this with our current compute technology. So no problem. We are not hitting the Landauer limit as a physical constraint. However, there is another limit that we are hitting, and this is the electrical data movement, because we still, on chip, we still move data electrically. So it means that there are metal layers between 10 and 15 typically on today's chips. And these metal layers, they have physical properties, of course, and the energy loss on this metal layer is proportional to the resistancy of the metal layer, so and a constant depending on the material of the layer times the length. So the material constant we cannot change. But we can change the length and the cross-section area. So the length is the size of the chip. This is not changing too much either, because the chips don't go too large. I mean, they grow in size, but it's okay. It's not a factor of 2 every year. But the cross-section area is now this size, and we divide by the cross-section area. So as we scale down our process, the overhead of electrical data movement in terms of energy gets actually larger. Interesting observation. So not so great. This is what gets me through the 3 L's of modern computing, which is basically spatial locality, temporal locality, and control locality. So it's all about locality. This is probably the main takeaway from this talk. Like, it's all about marshalling your data. And there's a a very good survey on this that you could look at, also already a couple of years old, that describes how we deal in these data locality abstractions in HPC systems today. Was it TPS? Gee, I'm removing my mask now because I'm going to suffocate. So, so this control locality is something that is actually a very interesting concept if you think about it foundationally. So if you look at von Neumann machines, which is what we're using today, what my watch is, and what basically every computer is that we use today, the way it works, we have some memory, we have some arithmetic logical unit, we have some registers, we have some control pieces, and this is the crux. We have some cache that plays no real functional role, but it's good for performance. And we have some data path and the control path in that system. And what now happens is that the control path is loading operations encoded in data as data in the control logic that orchestrates the arithmetic logical unit and all this path here, as you can see. So it's going up and down. What this means, in order to execute one addition operation, in this case here, we require 70 picojoule of energy. But unfortunately, the actual addition is just this small piece. So it looks like it's smaller than 4 or 5% of the overall overhead, which is the iCache axis, as I told you, right? There's very large overheads. Register file axis the same. And then the whole control logic that controls this block here. So now, this was already pointed out that this is very suboptimal in 1977. But the interesting observation is that after 1977, the long tail of compute scaling was going on. So every 18 months, like Moore's law, we had a doubling in the performance. And we didn't really care about this. We never cared about fixing that bug. Because we could just wait and it would get better. And we focus on having new insights and new technologies. But now the problem is Moore's law is over. So we don't really know how to fix these things. And now we have to face them. One way to face them is with a static data flow machine or architecture, where we basically attach the registers to the arithmetic logical units that are now specialized, right? So here's a plus, and here's a times for this very simple operation. And now we can just pipe these operations through this data flow unit. So this is the hardware of tomorrow. I tell you, we have to adopt to this thing. Unfortunately, which is going to be much harder. It's going to be much harder to program as we program today. But if you want performance, if you want low energy consumption, that is the way to go, or some ilk of this. Because here we have an energy consumption that's about 50 times lower as what we are used to. And the only problem here is how do we program this beast? But this is what I mean with control locality. Now you could argue, oh, GPUs and vector units fix all of this, because what they do is they control many ALUs with a single control path. That is very true. What actually happens is that in the single control path, I now control, let's say in this case, 10 ALUs, or we could even have 100, with a single operation. That reduces your operational overhead. But remember the data access overhead. You still need to read, each of these ALUs still need to read from a relatively large register file. If you look at an A100 or a V100, you see this is up to kilobytes, multiple hundreds of kilobytes of size. So compared to that architecture, again, here I'm paying, let's say here, 20 picojoule access per time, per floating point operation, while in this architecture, I'm paying 0.1 picojoule. Right? So huge 200x benefit. So we still have a lower control locality here. So really what happens in high performance computing is that it's all about managing the data. Because this architecture is very similar to this architecture, just with the only difference that the data has to be at a certain time at a certain place. And this is what I would call spatial computing. And we have to make sure that we don't have this flat model where we read registers, arbitrary locations in registers. No, we have to ship the data through the system. This even improves performance on today's systems. So this is why I'm saying it's really a data management challenge. Forget about flops. That's the other one. Forget about flops, please. So data movement will dominate everything. The DOE has actually realized this based on the energy consumption observations. And there were multiple papers and plots on this. There's actually one lighthouse paper that's a couple of years old from Shaker and Andrew, and they write about the future of microprocessors. And they didn't think about it, that it was a data movement problem at the time. Otherwise, they would have called the paper, Data Movement is All You Need, which is the title that we chose for our latest paper. But in this paper, if you read it carefully, what you find is that data movement shows up 18 times on the 11 pages. Like it's kind of subconsciously, because when I talked to Andrew about this, he was quite surprised to hear this. I was like, oh, okay. And then there was one key sentence in here that the future of computing basically will depend on sophisticated software to place computation and data so as to minimize data movement. Okay, so now the question is, what is this sophisticated software? So how do we program today in this sophisticated software world? Well, to a good approximation, we program like we did program yesterday, or last year, or actually more like 4 decades ago. So really, we do program like Bacchus was complaining about in 1977, unfortunately, because we are in a control-centric programming mode. We worry about operation counts. When you go to school, when you go to university, people will tell you about count the operations. Flops is the metric. We have the top 500 list. Everybody cares about flops. Data movement is at best implicit. So this is something that we need to invert now, because the times where the flops are expensive are actually over. You will see this later in the talk. It's all about moving the data. Legion has recognized this and is making some steps in this direction. I don't want to go into too much detail, but the idea is basically that it doesn't go far enough. We have to go much, much, much further. And what we want to do is we want to fully transform the view of the community towards an explicitly data-centric viewpoint, so that we don't count flops, but we count data movements as the critical, most expensive operations, at least for performance engineers. So how do we do this? So we developed this DAYS parallel programming framework, and now you probably know it latest if you didn't recognize me yet, who I am. But the idea is really that the domain scientist phrases his or her problem in some very abstract way. And we chose Python because that's kind of a nice way to phrase problems, at least for us. And then we translate this into an abstract representation of the program. Then we have a completely separate role once we translated the domain problem into this abstract representation, which is what we call a stateful data flow graph, where the performance engineer is actually working with. So this is incredibly important. There are 2 different people, or 2 different roles. It could be the same person fulfilling these roles, but we really separate between these roles: domain scientist and performance engineer. Very often these are not the same person, what I'm observing. Very often the domain scientist is, I don't know, a marine, probably at KAUST, somebody looking at the health of the ocean, while the performance engineer is more like a computer scientist or an electrical engineer building architectures. So the performance engineer is then using graph transformations, and then at the end we have an execution system where we run on. So in other words, we take a Python input, compile it to internal representation, which compiles it to a C++ output, which then runs on a CPU, a GPU, or an FPGA. So you could also be excited about the fact that we have a Python to C++ compiler, a limited Python to C++. So finally, Python is kind of fast. But this is not the research point. This is just a side effect. But let me explain this a little bit more. So we have a domain scientist that has this equation in mind that he or she wants to solve efficiently for a very large vector of x. So what does the domain scientist do? It wraps it into the data-centric formulation, where actually all he or she specifies is the input, the x, and the output, which is f of x, or we call y here. And then we can forget about the equation. This is something absolutely wonderful, because I have a history as a performance engineer. I was actually at NCSA. I was leading a team of 12 very qualified people. You do not necessarily want to understand the computation that the domain scientist wants to do as a performance engineer, because you don't have the time to understand this. What you want to make sure is that this computation runs fast. And this is the main task. And what we believe is that you can ignore the details of the math. All you need to worry about as a performance engineer is the inputs and the outputs and the data flow. And then you can do, and we call these things memlets, by the way. And then you can do nice things. You can vectorize, because of course you get many inputs and many outputs and not just one in the average case. And you can parallelize immediately. So you don't worry about the code in here. The code is just a black box essentially. And we just replicate this black box. This is something that's very, very popular in the machine learning environment right now. So this is how PyTorch and TensorFlow execute. But first of all, we started our project earlier, but well, they have slightly passed us with more resources. But this is something we should also bring to the high performance computing community. So this is one way to look at the problem. And then what we do is we actually, because this is quite an annoying representation, we draw this in a different way. So we have a specific format that we call the stateful data flow graph that also comes with a graphical representation where we represent a loop as this, what we call burger thing. So there's an upper bun and the lower bun, which is the loop begin and the loop end, and then the tasklet somewhat in the middle, and all the data flow is visible. So this is a very simple example here. These get much more complicated. And this is what we call stateful parallel data flow programming. And then, of course, you could have multiple of those. So A produces B, but then later we want to overwrite A again. And if you're an expert in data flow, you will realize, oh, that doesn't actually work. I cannot have a cyclic dependency in a data flow program where I read A and write A. That's not working. So what we do in this case, we introduce two different states, where in state 0, we have a true data flow graph, and in state 1, we have a true data flow graph. And then in between, we have state transition edges. To make this a little bit more concrete, for example, if you have a 2D stencil, you have an initialization part where you write an array B. Oh, this should actually be A here. I'm sorry, this is a typo because here A is consumed. But you write an array A. And then in your first iteration, then you're actually reading array A and apply a Jacobi to it. But you have to make sure that the reading of the array happens after the array has been initialized. Right? This is why the initialization is in state 0 and then state 1. And at iteration number 0, we go from, this is the start state, we go from state 0 to state 1. And then we iterate in state 1 until iteration number t. Right? So this is the very high level. So we could actually look at code. I don't have enough time. I would love to do a demo, but Hatem told me that I only have 45 minutes, so the demo has to suffer from this. But actually what you can do today, actually now if you want, if you find the talk boring, go on, open a shell, do pip install days, and play with it. So this is all open source available today, and within 5 minutes you can get some programs going. I apologize in advance, it's research quality code, so there will be some small bugs that we know about, and we will fix if we get the time. But if you look at the code here, it's basically exactly like this. You define a Python function, you decorate it with days.program, and then you have to have some special syntax here that allows us to extract this graph, telling us some things about your function, basically. And then we can transform it automatically into this graph. And then we can apply transformations, as you can see. Let me go back. Where we have this graph, which is the slowest possible matrix multiplication you can imagine. This is basically the 3-loop, very simple matrix multiplication, right? So we call this multiplication on m, n, and k, and we multiply these two, and then at the end we just reduce into the same value, just a slightly different syntax. You can see this is incredibly silly because this needs n to the cube memory. But we can have a transformation, which now the performance engineer implements that gets us way down to n square memory. And now let me introduce the elements a little bit more. So we have containers, we have computation, we have data movement, and we have parallelism and states. I've implicitly already explained all of those things, but this is a little bit more of a formal overview of the language elements we have. And as you can see, it's a graphical language. And so this is quite important because for data flow, you need to understand this visually, where the data flows, because otherwise it gets too complex to understand. We have a wonderful user interface where you can look at the source code, transformations, the SDFG itself, so the graphical representation of the program, and you can actually look at the generated C code and the performance. The generated C code is, of course, harder to read than the source code in Python or the SDFG. Yes. So now let me go through a case study, a matrix multiplication on x86. So this is the SDFG of the code I've shown you 2 slides ago. This executes with basically 0 performance. In fact, it has n-cube memory requirements, so you can't even scale it to a large memory size, to a large problem size. The very simple transformation I showed you increases the performance negligibly, but gets us to a very large input problem size. It's just, we fuse 2 states basically. But then we can apply more and more transformations automatically. Like I could go through through our code and show this in a couple of minutes. And then we achieve about 75% of Intel's MKL for matrix multiplication. Actually, if we tune this further, we can get to 98%. But Intel's MKL pulls some tricks in that it optimizes for specific matrix shapes and all of these things, which we don't. But I don't think we care about matrix multiplication on x86 CPUs unless we want to implement LinPack, but that's not our goal today. So we want to actually go a little bit wider in what we do. So let me go a little bit faster here. So we can generate code for various architectures, and I don't want to go into detail. For example, load store architectures like CPUs and GPUs. But I also told you that at the very beginning of the talk that we need to be prepared for data flow architectures and pipeline architectures. So we can do that as well. We can actually turn your Python code into a circuit, and your circuit can then execute on an FPGA in various configurations. Or you could actually take your circuit and you could run it, or you could print it, you could send it to TSMC. If you have about $50 million, you could get a 5 nanometer chip printed with your circuit. If you don't want 5 nanometers, if you're fine with 45 nanometers, then you can get it beginning from $10,000. So this is actually not too far off what some people do with machine learning accelerators. So you could design your own machine learning accelerator very quickly. If your market is big enough to get you a return of about $10,000, you can print your own chips. So we evaluated this. Of course, we don't print our own chips. We're a university. We don't have enough money. We buy FPGAs. FPGAs are not great. So we basically evaluated it on CPUs, GPUs, and also FPGAs for performance portability. So here you see all the data. We compared it to the latest in 2019, so basically 1 year old. For some fundamental kernels on CPU, we get reasonable speedups. So we even beat MKL in a case where MKL is not so good. So sparse matrix multiplication is really not so good. Yes, for sparse matrix vector, we get actually very close to MKL. So we don't beat MKL here, I was wrong. So we get very close to MKL with an automatic tuning framework starting from Python code. And then we can also compare ourselves to NVIDIA, where we get 90% close of Cutlass, which is the open source version of, or an open source BLAS implementation of NVIDIA. For FPGAs, we look much better because it's much harder to get performance in FPGAs. So we beat Spatial, which is a tool by Stanford University, by a factor of 20. And even better, on Vivado HLS, we beat by a factor of 309,000 times. That actually led to rejection of our paper because the reviewers thought that is ridiculous. And so we removed it from the later version of the paper. But this is actually the speed up we get. So over a normal C loop translated in Vivado HLS. So then we also ran all of Polybench. You may or may not be interested in this. You can look at this at the paper. We basically beat on CPU Polybench by about 40%. We were the first to ever translate all of Polybench, which is a CPU benchmark, to FPGAs, right? So to really design circuits. And it gets better, but fine, let's not talk about micro benchmarks. Let's go a little bit further to the actual goal of our research. We wanted to make the world of domain scientists and the world of performance engineers both stronger and more intuitive to program. Domain scientist writes at Python, performance engineer, engineers in the data flow world, right? So I didn't show you much about this yet. So let's go into one specific case study of quantum nanotransport simulations, which I'm not an expert in, so I can show you these colored pictures. And one of my collaborators, Professor Louisier at ETH Zurich, could explain what they actually mean, but there are more colored pictures. And just believe me that this is a very relevant problem. It's actually relevant enough. The code was tuned very heavily. There was a Gordon Bell Award finalist in 2011 and 2015 in both years. So it's about 90,000 lines of code. It is solving a Green's function on the electrons and phonons. It iterates between electrons and phonons through the self-scattering energy. Is really something where you probably most of you understand these equations better than I do if you have a computational science background. And it has an extremely complex data distribution that I just want to not explain. I could, but that would take half the talk. But I just want to show you an animation that shows for the number of electrons and the number of K points here how this data actually has to be distributed to the machine at hand. In fact, one of these Gordon Bell finalist papers was about nothing but how to orchestrate the MPI program to run this complex data distribution. So in fact, they used MPI functions that I was always wondering, why would you use those MPI functions ever? And they found very good use cases for those, very complex collective use cases. So this is relatively complicated, too complicated to explain now. So what we now did is we looked at that code, 90,000 lines of code. With the help of a postdoc of that particular group, we translated this into a high-level SDFG view. So we collapsed all the tasklets here because otherwise it would be too large. And now you can actually see how the data flows at a very coarse grain. And let me just focus on self-scattering energies because that's what consumes 90% of the time. And then we could look at the decomposition that was in that Gordon Bell finalist from 2015, which basically adheres to the natural view of the physicist of how they write their loop order in their loop. So it's pretty obvious that as a physicist, you first want to have atoms, then first want to have K points, sorry, then you want to have atoms, then you want to have your orbitals, and only then you want to go down to quarks and gluons, because that's your natural physical order. And this is how you write your loop indices. But unfortunately, and these loops are distributed over 90,000 lines of code, right? So this is something that's basically impossible for a performance engineer to refactor because they're in different files. They're completely distributed in a code that employs Fortran, CUDA, and C++, all mixed into various modules. What we did is we looked at this from the very high level, and we found that the natural loop tiling is actually pretty bad for performance. It's very nice if you're a physicist, if you want to understand your code. The loop tiling that we chose is extremely unintuitive for the domain scientist. So even if I would take your code and retile, optimize it for you, change all these loops, you would have a hard time understanding it. So this is a horrible disaster, basically. You would not be able to change your code anymore. This is why we want to make sure that the code that the domain scientist sees remains intact. And then we do the loop tiling underneath based on the data flow principles. So it looks completely different. And again, I don't have time to explain, but the interesting thing is the number of MPI invocations went down from 9 times the number of, I forgot what W was, times the number of Q points down to 4. Right? So there's actually all this multiplied together here, all these sizes. We were able to pull them apart into sums, which is significantly smaller. So what happened actually, the communication of this code was reduced from by more than 100 times, actually up to 250 times at a very large scale. So from petabytes to terabytes communication. So we had some interesting additional insights, which are quite trivial. Python is slow, we all know this. If you write this code in Python, you're basically dead. So you're losing a performance factor between 10 and 100. Kublas is extremely inefficient for some executions. And then we scaled that code on Pitstein and Summit. So I just want to show the Summit numbers. So if you look at the computation of the original Omen code and the communication of the original Omen code in the share of the overall code in the strong scaling case, our day's code got much faster in the computation just because we generate better code. And the communication is basically 0 in this plot because it's the 100 to 250 times savings that we could do. Also, we were able to scale to 10,000 atoms, which is something that the scientists were just dreaming about at the time. And at the end, we achieved about a 100x speed up, putting everything together over that code. And that got us the Gordon Bell Prize at SC19 last year. So, and basically the insight was data movement is all you need. We optimized only the data movement, but at various scales. We optimized it at the global scale, we optimized it at the local scale, and we optimized it at even the register assignment scale. So I could explain you that diagram here, how these SDFGs are mapped to specific registers during the execution in order to implement the gem function, or basically this add operator, which is in NumPy, it goes to the gem function with some strided small matrix multiplications. So this you can all do as a performance engineer in the view of the SDFG. Of course, this was all put together, so it's not as perfect as it may sound. So if you download the code, you can actually reproduce this experiment if you want. You will find many, many small pieces put together manually in MPI 4Pi. So it's not the framework is not ready yet, but it's much better than it was last year, in fact. So now I want to get to a second application class, because now you could say, oh, these guys totally over-specialized on quantum nanotransport simulations. Quantum nanotransport simulations is probably a simple problem. Even though I would like to not say this, but let me go a little bit broader and say, well, there's a second application class, which is quickly emerging, which I would call natural knowledge representation, formerly known as natural language representation. But I think where this field is moving is really towards knowledge representation instead of language representation. So these are these models that you may or may not have heard about, where people investing billions of dollars. So the company Microsoft has pledged a $1 billion investment in building an AI supercomputer. And much of the purpose of the supercomputer is actually to run models like this OpenAI's model, which is the big partner of Microsoft in that endeavor. And they run a model that they call GPT-3. This model has 175 billion parameters. So just in FP16, this is going to be already multiple gigabytes, hundreds of gigabytes of data. The single training of this GPT-3 model is estimated to cost $12 million, the single run. Oh, the interesting news is they had a bug in their code. They could not retrain it. Sorry, bad. This is like a major endeavor, like launching a space shuttle, basically. You could compare this to launching a space shuttle, to just train a single AI model. And a paper comes out of this. Now, that's a $12 million paper. You can download from arXiv. It's a very interesting paper. I could go much into detail, but we can probably have a discussion later if you want. They go very much into detail of the time to train this model for these 175 billion parameters. By the way, our brain probably has 100 trillion neurons, or more like 80 trillion, so much more. And then I'm covering this on Twitter, so now you know my name. Okay, I did not remove this, I'm sorry. But hey, I lasted until 80% of the talk. If you want to know more about this, I have an analysis of this, this GPT-3. So actually to train this, it requires 314 zettaflop operations. And so we're still talking about exaflops as a goal in HPC, but AI is already at zettaflop. Of course, this is FP16 and FP32, right? So this is a much lower precision, but still it's completely crazy. So for a single GPU, this would take 155 years to train. Or actually, it would use about 400 megawatt hours, right? So this is completely crazy if you think about this, the cost. Now comes the even crazier piece. Google was like, oh, 170 billion parameters. Well, you know what? We can do 600 billion parameters. And actually, they wanted to go 1 trillion. But the 1 trillion parameter model failed. So it ran out of numerical accuracy, which you could now imagine. Actually, if you know the architecture, it's not too hard to understand. It gets too long and the gradient vanishes. But this is just the latest and greatest thing from June 2020. So a couple of weeks old. And I was also covering this. It was actually my most successful tweet ever. So this is a 2 terabyte model. So in order to ask this model anything, you would evaluate a 1.2 terabyte data set, basically, completely crazy. And they measure the performance in TPU years. Right? So in the paper, they measure in TPU years, which is also something to get used to. It's quite funny. And the model needs about 37 zettaflop, actually less than the previous one for various reasons, because they go sparse. So this is something that we could also discuss in the question session. But now, some interesting thing that we looked at is these networks, these 2 networks I showed you about, or both of these papers, they use networks that are called transformer networks. So transformer networks are probably the computationally most expensive single single simulation or training run that we do currently. So in my lab, we looked at optimizing these transformer networks, because of course, if I can make this thing 10% faster and it costs $12 million, then I can validly go to Microsoft and tell me, hey, pay me $1.2 million, please. Unfortunately, we do this all open source, so you can just download our thing. You don't have to pay us. But what we found is that all the existing implementations really inefficiently use GPUs. So they only get about 30% of peak flops. Actually, that was found before. But what we really identified is that the key bottleneck here is the data movement. Again, coming back to the original thesis. Why is that? Well, you may, if you look at these transformer networks, they're all matrix multiplications of one ilk or another. It's actually a little bit more complicated. It's tensor contractions. So they contract 4-dimensional tensors to 3-dimensional ones and 3-dimensional ones to 2-dimensional ones. And only the 2D ones are then matrices. But it's basically the same operation. So you can express this as matrix multiplication. In fact, they do this in cuBLAS. However, these matrix multiplications are optimized so much with these tensor cores that if you look at Amdahl's law, if you make the matrix multiplication very small, something else will be your bottleneck, the matrix multiplication overhead very small. And this overhead is now data movement. And now we could go through the data data flow graph of this operation. So this is the multi-head attention operation. It's kind of the heart of a transformer network. In fact, this is part of a larger operation. And in fact, imagine this whole block that I'm showing here, somewhere between 32 and 500 times replicated. Right? So this is the depth of the network. So this is the basic operation. This is the basic block. I don't have time to go through this, but I want to give you some highlights of what we found. So one highlight is that these are tensor contractions all here, right? These operations in here, tensor contraction, matrix vector addition, tensor contraction, kind of a statistical operation, softmax. Tensor contraction, tensor contraction, tensor contraction, tensor contraction, tensor contraction. So it's basically all tensor contractions. For these tensor contractions, where you employ matrix multiplication, based on the layout of the matrix, so based on which dimension is first, or what's the order of dimensions in main memory, your performance may vary somewhere between 2x and somewhere between 10x, as you can see here. So these are basically peak performance from 0 to 100 for different layout variants of these matrices. And of course, you want to always be at close to 100, so always at the best. But now, if you go through this complicated graph here, the output of this operation will not be the best case of the input for the next operation. No. It'll be something else. So now you need to solve an overall optimization problem to find the best case that goes through that whole graph and does not transpose the matrix at every single step or the tensor. Right? So this is one interesting property. What you see is that actually in these tensor contractions, we spent 99.8% of the floating point operations. Okay, so it's really all tensor contractions. If you look at floating point operations, if you're an old school HPC person, you would be like, okay, let's optimize these tensor contractions. That's what NVIDIA did. They made these tensor contractions very fast. They have tensor cores now. However, unfortunately, it's only 60% of your runtime. Oh, that's bad. Amdahl's law. So I can gain at most 60% if I get that down to 0. That's extremely bad, actually, because now I invested all my money into making tensor cores, but it's not really the tensor core that the thing is, because it's the statistical normalization. The softmax thing is now popping up. It was completely not visible before, but now, of course, it's like this whack-a-mole. It pops up. So one insight. So basically, this is basically the central insight that we are now limited by the data movement and operations that are data intensive. So with that, I would like to close my talk and give you a little bit of an overview. So I talked about the fact that high performance computing is really a data management challenge. So this is completely changing our view. We have to adopt a new view. We have to change our teaching. In fact, I'm reworking the curriculum at ETH Zurich to make sure that we are teaching about I/O complexity for performance reasons. Because right now we teach complexity relatively wrong, I would say. Of course, I have to be careful with my colleagues, but in my view, computational complexity does not necessarily reflect reality on chips. So then we introduced this data-centric parallel programming framework that I talked about. This is all implemented. You can actually try it. We switched to VS Code currently. We looked at some kernel performance. We looked at a case study, 2 case studies actually. One was this quantum nanotransport simulation, and the other one were transformer networks. And then we showed that we can implement both of these case studies significantly faster. And with that, I want to conclude my talk, and I'm open for discussions and questions.
Great, thank you so much, Torsten. Let's give him a round of silent applause.
Wow, there's a yes button.
Great. Okay. Do you have any question from the audience? Please feel free to ask the speaker a question.
Torsten, if I may, I'd just like to, well, first of all, thank you so much on behalf of the group for showing up at our group meeting and delivering this amazing amalgam of last November's SC and then your breathless overview at ISC, which I think was the hit of the conference. And I'd just like to make a whimsical observation. You've chosen a Beatles allusion. SGFG is all you need, you know, from their Love is All You Need song. And I propose you choose an Andrew Lloyd Webber allusion from the song Love Changes Everything. SDFG changes everything.
That's a good one. Okay, very good, very good. You'll get credit.
You know, this is like a sweep of computing history, going from, you know, classical language, Bacchus stuff, all the way to next generation AI, and it's just mastery. And everything that you've said, we will have to study in offline, and hopefully be one of your propagation engines in the ECRC. I'll let my colleagues go back to your thing with specific questions, but thank you so much.
Thank you.
We have a question from Sameh. Sameh, yeah.
Hello, thank you so
Yes.
much for this presentation. I like it so much. And actually, during the last or several last weeks, we had a lot of presentation at the same time, and all of them is talking about data management.
Mm-hmm.
Okay, so it seems that now everyone is looking to data management,
Exactly. Yes.
actually from the software side or hardware side. So it's good to hear this again with the computer science oriented presentation. I have one question about your data-centric parallel programming. I cannot understand how it's different from existing task-based runtime systems, for example.
Mm-hmm.
Because even you are using the same language, you are calling tasklet. They have using, for example, in StarView, they are using codelet. So you are using the same words.
Yes. This is a very important question. Yeah. So the difference is actually twofold. So one is the current tasking frameworks. They are only now looking at how to minimize communication or data movement. So they started out on how to distribute tasks better to do parallelization at various grains, and then later they went to how to do it more heterogeneous, and now they're looking at data movement. So we are data movement from the get-go. But this is not the main difference. The main difference is really that if you program for one of these tasking frameworks, you have to pick a task granularity, right? You have to implement your task, which in our case, because they don't include a compiler currently, they're just a runtime. In our case, we force the programmer to tell us a multi-level sizing of your tasks. So basically we tell the programmer, give us the smallest possible decomposition into tasks that are single operations. And yes, I didn't make this very clear, but a tasklet for us is basically a plus or a minus or a times, so a single operation. And what we do from there automatically in the compiler, we coarsen it as much as we need to for the specific target device. And that's incredibly important, because if you now, this is what gets us the performance portability. You can write one code and we can translate it to CPU, because on a CPU, you need relatively coarse-grained tasks because you have not so many cores today, right? But they need to do register tiling, and they need to do a very structured vectorization, right? But we can take your same code with the same expression, very fine-grained expression, and run it on a GPU, which is the complete opposite of a CPU, because you need very fine-grained tasks. Right? The device needs to know all of those tasks. There, the plus is actually a single operation, and run it there. We can also take your tasks and turn them into a pipeline on an FPGA or on a piece of silicon. This is the major difference, right? So you don't have to implement these tasks for specific devices, because we derive them automatically based on this data-centric view. And we can do it because the language we force, and there's no free lunch, right? So there's some catch here. We force you into a language where you have to tell us everything about your task dependencies. This is the data-centric. And most tasking frameworks today, like if you look at OpenMP tasks, for example, you write those in C. And in C, as a compiler, I cannot derive my data dependencies. So we just force you to give them to us. While in other task frameworks that I know, there is no chance that you could get those data dependencies. Right? This is the fundamental difference. This is where it gets to language design, as David Keyes was pointing out, where we're bleeding a little bit into this.
Thank you so much.
Yeah, thank you for the question. That was great.
Perhaps a follow-up question. What about one API? Right, you mentioned performance, portability. You mentioned right language compiler support for doing all those locality-aware, development. What about how does it compare and differ with one API?
Oh, one API is an absolutely wonderful project. So I'm in heavy support of it. The idea is really nice. So they basically take a SYCL, or what they call DPC++, and make it portable, functionally portable, and this is very important, functionally portable to all these different devices. And this is an incredibly value for the community, because right now when you program an FPGA, it's a total mess. Okay, one API's FPGA backend is okay. But you now need to only learn one language to program all these devices, and this is DPC++. However, they have never said that they would be performance portable without code changes. So for even in one API, you would still need to optimize your code for the specific target devices. Like you would need to add pragmas for FPGAs. You would need to change your code to run effectively on GPUs and CPUs. So it's not vanilla performance portable. While we go one step further as a research project, and the obvious idea is now, like, once we solve all these problems, that should feed back into efforts like one API. And that would be wonderful if they would take our results and extend their compiler to deal with this data flow modeling. But right now the goal is not as glorious, but extremely important, to have portability, functional portability across a very wide range of architectures. Right? There, the goal is very similar.
Thank you. We have a question from Kadir.
Hi. Thank you, Torsten, for explaining all these problems in a very formal and unified way. And my question is, did you test this against the native batch calls of NVIDIA or MKL? Because their batch calls are also increasing control locality. You are able to catch their performance?
So
or will you?
Yeah, this is where some of the slides had some information on it, but not too much. And I was going too fast that anybody could actually follow those. But for example, here, to give you the most interesting result, so the answer is yes and no. For some kernels, we actually reach the performance of cuBLAS, for example. For most kernels, I would say, we reach about 95% of the cuBLAS performance. For some kernels, we are significantly worse. For some kernels, we are actually significantly faster. And here in this particular case. So if you look at this implementation, these are tall and skinny matrices, essentially. And if you run those, and I don't have a visualization, but these are tall and skinny matrices. And if you run those and you just measure the performance, you will actually achieve 86% and 84% peak on the P100 and V100 respectively. However, it turns out that it seems like NVIDIA is padding quite heavily, because only 6% is a useful flop in these tall and skinny matrices. So it looks like, we don't know the source code, but it looks like they're probably turning these tall and skinny matrices into more square matrices and then process some zeros. And what we could do in this case, we could use days to implement a new library call for this. And so there we got significantly faster. So in the V100, it was even nearly a 5x benefit, as you can see here, for the same operation, even though we only achieved 28% peak. Right? So this is one of those things, if you floptimize, if you want the maximum flops, then this is great here. But if you want the maximum useful flops, then this is not so great. Right? Because that was actually an interesting thing. My students, they benchmarked this and said, oh, this is a great function because it achieves 84% peak. We cannot optimize this. And it took us quite a while to understand that no, don't look at this peak performance, look at the actual runtime.
Great.
And there are some more examples like this.
Yeah, thanks.
So I have a question. What do you mean by the useful percentage?
Oh, I mean that of this 84% peak performance, most of those are multiplying zeros. So when they take the two tall and skinny matrices and you add some zeros to make them square or more square, then you could actually call your optimized implementation that is optimized for square matrices. Right?
Okay, got it.
But many of those would multiply by zero. Of course, that still runs really well because you now can go into your case where you have optimized for.
Right.
So you get a high peak performance, but most of those are not adding anything to your problem because they're multiplying zeros and then adding the zero to the result. So it's equivalent, but kind of wasteful. And so that's what we've observed.
And like these can't be ignored, like instead of them being calculated, or then we're back to the skinny matrix.
Well, they're still processed. Yes, I mean, this is what we are doing basically, but the library they call, the code does not ignore those. Right? So the it looks like, again, we have no access to their source code, so we can't tell. But what we observed is that they get very high peak performance, and they process much more flops than we do. And so some of them must be useless, right? Because if we can solve the problem with 1/10 of the flops, so obviously if they do more, then it's not helpful. But this is pure speculation, so I don't really know the details of the implementation.
Right, thank you.
The question from Bilal.
Yeah. Hello, good afternoon. So I don't know if I shall call you Sheikh Torsten or Prince Torsten. Very nice. So thank you for this great presentation. I have a follow-up, and this is sometimes like some of the people working on the application, they share some concern about portability, going to a different hardware in case of the accuracy. So with this portability, what about the accuracy? Is it preserved, or can you elaborate on it?
So what we do for the pure data flow optimizations, it's exactly the same accuracy. However, the nice thing, what we are trying now, this is ongoing research. Since we have the framework under control, the execution framework, we can actually play with the data types. So what we did for, do we show this here? So if you actually read the Gordon Bell paper, we tried to go down and use tensor cores for this particular problem, for this quantum nanotransport simulation. It turns out that the benefit we got out of the tensor cores was about 5%, if I remember right. So basically nothing. But the nice thing about DACE was it was very, very simple to implement that experiment. So tensor cores are not too useful for many computational science applications. But you can get another 5% for some cases relatively easily if you want to. The interesting insight is that this machine learning stuff is all tensor cores. Right? So nobody here uses more precision than 16 bits unless it's an accumulator. But these are not, the vast majority of the flops are actually 16-bit flops. So you need to, I think in the future, what we need to understand is, so we can stay bit reproducible, that's fine, we can do this. But I don't think we want to, because everybody is going to build low precision hardware. We as a computational science community need to figure out how to use it. And I know one of your previous speakers was also giving a long speech about this. And we have the framework to do it. Right? Transparently, you can basically, with the transformation, change the data types in the SDFG. And by the way, my outfit comes from my last visit to KAUST, which is now already 6 years ago. Actually, my only visit, the first and last. So
I still remember, like you and Rio in the same store, I think.
Yeah, and Hatem was really good at negotiating a good price. It was all in Arabic. I didn't understand anything, but
Great.
We look forward to seeing you back here at KAUST for face-to-face, let's say, similar.
I would love to.
Thank you.
Torsten, I have a question on one of your slides where you make the separation of concern, domain scientists, performance engineering.
Yes.
And it's just a comment and perhaps some of your feedback also. The performance engineering aspect sometimes is not really well acknowledged or well, promoted or well, given a good, justice, right? I mean, you see what I'm saying, right? So, I mean, even when we talk to domain scientists, they're not that excited when you come to them and say, okay, we're going to make this faster. Yes. Okay, and then what, right? Or why bother, right? Or,
yes.
I mean, what can we do? I mean, in HPC on, to better perhaps, attract or sell what we do, to more domain scientists. I mean, I had a discussion, for instance, a few months ago in one of the meetings for Shaheen 3, and one of the big users on Shaheen, CFD guy, telling us that, this is all great, but, since, selling a new data movement, for instance, optimization for my code in CFD, they don't care less, right? They don't care less about this thing. So what are your thoughts on this?
I could give a 2-hour speech on this, but let me make it very short. So I completely agree. Yeah, this is the observation. And the observation actually stems from another fundamental observation is, how do scientists get compute hours? The way they get compute hours is they write an application and then they get 1 million compute hours or something like this, basically for free. And if they need more, they can apply for more. So they don't actually see a direct connection to the cost of what it costs society to create these compute hours. So this is partially a bit of my concern, because sometimes I observe scientists using these compute hours relatively carelessly. So if we change that model, and I think it will change, by the way, because more of compute will move into the cloud, and the cloud is very transparent when it comes to cost. Right? So it's not like the computing center where you never see the bill. I mean, at the end of the year, it's like for CSCS, it costs 25 million, but it's not really clear how many million of that go on my account. So because we count in CPU hours, it's a very different metric. And the problem is the engineer that then implements, the performance engineer that implements these optimizations, that person costs dollars or whatever currency you want. And that is now a problem, right? So we have two different ways to actually account for this thing. This is the fundamental problem. So now the question is, how could you get a carrot to the domain scientist who may not care? It's extremely hard. Actually, I mean, in the current model, I think the only way you can convince a domain scientist to care about performance is to give that person a new capability, right? So for example, with that quantum nanotransport simulation, you can now simulate a system that is 100 times as large as it was before. And that is a qualitative change for them. Then they will say, oh, now we invest because we got that scientist to invest a postdoc for 1 year into rewriting the code, right? Actually himself as well. So it was more like 1.5 people, 1.5 FTEs. And for him, it made the difference because he can now solve bigger problems, which were just intractable before. I think the make your system more efficient argument, really people don't care, absolutely not. And it's not the domain scientist's job to care about this. This is let me be explicit. I don't think domain scientists should care about it. So today, who cares about performance of the system? This is the operator of the system. The data center operator, the owner, the guy who has to pay the bills, has to care about the performance. This is why all these performance engineers sit today in compute centers. Right? So in Switzerland, we have a large group that sits very close to the compute center. Bilal is very well familiar with that whole story. So this is something that these people care about this. So somehow now is the disconnect. How do we get the the domain scientists to write in a language, to potentially rewrite the code in the language that is now amenable to the performance engineer? There's no way that we can do this. Again, forget it. Like, they will not do this. This is why our idea is we tag into Python. So Python is the language they use anyway. Right? This is exactly what Google does essentially. So the people writing the models, the machine learning models, they have no idea about performance, like really, and they don't care. They care about capability, right? And they write it in TensorFlow and PyTorch. TensorFlow and PyTorch are very similar. You could say that DAP or DACE, our framework, is the TensorFlow and PyTorch for high performance computing, right? Because there they get this separation. So they have a herd of domain scientists, or they call them data scientists, that sit on top of the thing. They write, I don't know, their model, their deep learning model, the latest and greatest one. And then if that model turns out to go into production, so for example, BERT, the thing that one of these transformer models I talked about, is in production at Google. That thing runs inference. When I type something into the Google search box, you're running through that deep neural network. That thing is expensive. And then they have hundreds of people making sure that executes efficiently, because that is their business value. Like if they can offer an inference at 0.001 cent, that's how they make money, right? If it costs 10 cents, they make no money, right? And this is the whole point. So we need to get into that mode, and we need to enable it, right? So we could now, of course, say the Intel mode in order to, I'm sorry, I don't want to talk bad about, okay. The current performance engineering mode, like send me your code. Like I went through this. So send me your code and I sent you some code back that runs 10 times faster. Problem is you don't understand that code. And you basically throw it away after your system went through the acceptance tests. So basically that's an existence proof that that the system can perform at a specific performance, but it's not actually helpful for most domain scientists. So if we convince our community to generally adopt a model like we were proposing, not necessarily the same, but the separation of concerns model, where the performance engineer is clearly decoupled, then this is the big step. Machine learning has achieved that step. Machine learning has, by the way, achieved it because it's much simpler for them. They have a much more constrained problem space. It's very clear. I mean, I was able to learn it in less than a year. It's very clear what they do. In computational science, it's all over the place. Like so many different methods and approaches and groups and politics partially. So that's much harder to do. Sorry for the long answer. That triggered a point that I think is important.
Thanks for your feedback and comment. Any other question? We reaching 3:30 local time, I guess.
Yeah, can Torsten go to the first page, to title page, to take a picture?
Which page?
Oh, the title page. I need to take a picture for the whole group on the title page.
Oh, I see. Well, this is actually, in my thing, it's the last because it was less, because it was anonymized. So that guy here. Yeah, I mean, if you Google for my name, I'm the director of the lab who does that.
We know you very well.
Okay, that's easy. But it's extremely important that all the work that I talked about is really not done by me. I'm giving this direction. So this is really the team here. The development of DAYS, for example, is led by Tal and all the students here. So this is a huge collaborative effort. So I'm just complaining about about things that don't work.
All right. Okay. Well, thanks everyone for joining us today. I'd like to thank the speaker again, Torsten Hoefler, for joining us on a Sunday. I realize that it may be difficult for some of our collaborators to join in on a Sunday. Plus, he was on vacation, so I really appreciate your time and effort to join us today. And well, thanks everyone, and I guess we'll see you soon.
Thank you. Bye. Hopefully see you in person.
Thank you.
Take care. Bye-bye.